Happy snow day. Excuse me. Hopefully this works better than it did the day that I was out. But here are some things that you need to know. So the first thing I want to talk about is polarity, because I've gotten a lot of questions about molecule polarity. You guys are really great at bond polarity, right? Bonds are polar if there's a difference in electronegativity greater than 0 between the two elements. So if you've got carbon bonded to fluorine, it is polar. If you've got fluorine bonded to fluorine, it is not polar. Molecule polarity is the polarity across that whole molecule, right? So a CF is not actually a molecule. The molecule would be CF4. That's an F, sorry. And obviously there'd be dots. And because all of those cancel out, this is symmetrical nonpolar. And I know that Anna loves SNAP. So I thought it would be helpful, because you really need to get these polarities down before we move on to our IMFs, which is how we're going to wrap up bonding. But I thought it might be helpful to talk about what shapes are usually polar and what shapes are usually nonpolar, because there are a few that the shape itself will make it always polar. So let's talk about those. I'm going to highlight the ones that are always polar, and I'm going to highlight them in red because I just feel like red is polar and I don't really know why. Bent, okay, is always polar. Trigonal pyramidal is always polar, and bent here is always polar. Okay, I'm gonna have trouble with the linears, saying that they're always polar, always nonpolar, because that's gonna be depending on what it is. Okay, so like if you look here and you see that this guy is linear, okay, this is nonpolar, because the carbon is bonded to oxygen on all 4 sides. It's totally symmetrical, okay? Whereas if that oxygen were anything else, let's say it was sulfur, then it becomes polar, okay? The same thing is true here. We've got a C double bond, triple bonded, excuse me, to an N. This is polar. They're both linear, okay? But this one's polar. But if this were N bonded to N, like the nitrogen, if it were that, sorry, that would be nonpolar, okay? Does that make sense? All right, so carrying on with this, here we go. Seesaw is always polar. T-shaped is always polar. Trigonal planar is not, assuming they're all the same element, okay? Square pyramid is polar. Square planar, assuming they're all the same element, is nonpolar. This T-shaped is always polar, okay? And this linear, again, assuming they're all the same shape, is nonpolar. Hopefully that is helpful. If you do your drawing and you see, oh, you know, this is clearly seesaw, then you might be able to determine, hey, this is probably has a little bit of polarity to it, okay? All right, so the big thing that I need you to learn today / tonight is properties of solids, which I've kind of been avoiding, because sometimes I like to do this in the beginning, but then I feel like kids forget it, so we're doing it kind of here. So if you remember correctly, I asked you a while ago to leave some room in your ionic bonding notes. We talked about ionic bonds and how it's a metal and a nonmetal, and electrons are transferred. And I asked you to leave me 3 lines. These are the 3 lines that I wanted you to leave. You can put, I'm going to give you all the different types of solids here. You can put it back in those ionic notes, because I know I asked you to leave those lines. Or you can put it in both places. It's totally up to you. And I apologize, because I thought the snow days have thrown me off. Okay, so let's start with ionic. Okay, we know that an ionic substance is a metal to a nonmetal. Okay, ionic things, what I want you to think about, we've talked about this already, is salt. So typically ionic things have high melting points and boiling points. They are usually soluble in water. Okay. And very typically, they are not very typically, they're very typically soluble in water. Not all of them are, and we'll talk about that more when we do chapter 13 and 16. But what you really need to know is that this is the big tell for ionic, and I'm going to put it in a different color. How you know something is ionic is it conducts electricity when it's liquid or aqueous. In order to conduct electricity, you need to have moving charged particles. Ionic substances clearly have charged particles. They have ions, but they are in a fixed lattice, so they can't move. Water has movement. It's a liquid. Those things can move past each other. When you put those two things together, those ions fall apart, and they are able to move about the cabin, and that is why ionic substances conduct electricity. And then we're going to do network. Network things that you need to know. You need to know that all forms of carbon, just straight carbon, are network. That's usually going to be diamond, graphite, graphene, buckyballs, any of those types of carbon. Silicon, same deal. Silicon dioxide is a network solid, and silicon carbide. Those are those group 14 things, and what they are is a network of covalent bonds. I showed you a visual of this as well. What do you need to know about them? They have the highest melting points and boiling points. Think about boiling or melting a diamond, okay? They are not soluble. How about we say insoluble? They do not dissolve, we just said it, and they do not conduct. They're very rigid, okay? They're very hard. That's why we talk about diamond. Graphite is not as hard because graphite is in layers. Okay? Graphite is in layers, and those layers can kind of slide past each other. Whereas diamond is that network. I think graphite is carbon that is sp2 hybridized, I believe, and diamond is carbon that is sp3 hybridized. So in the sp2 hybridized, the layers can slide past because it's just those unhybridized p orbitals that are interacting, whereas for diamond it's an actual bond. You don't really need to know that. I do think you need to know that's why graphite is so soft, because those layers slide past each other. All right, then we'll talk metallic. I think we've talked about this one as well, but I want to cover it. Metallic has varying melting points. When you think of metallic, I always say pick the freaking metal. That's going to be copper, potassium, any metal, and it's just usually going to be a chunk of iron, aluminum. It's just going to be usually one thing. We will talk about alloys. Maybe I'll talk about it in this very video. Okay, metals have a sea of mobile electrons. That's usually what we talk about. And that's why they conduct as a solid and a liquid and a gas, etc. They're usually insoluble. Metals are malleable. What that means is that when you hit them with a hammer, they bend and they don't shatter. Okay, whereas an ionic substance is going to shatter, because as soon as those ions move a little bit, you're going to have a positive next to a positive and a negative next to a negative, and therefore it's going to shatter. They're malleable and ductile, meaning you can draw them into a wire. Metallic things sometimes form alloys, and there's a little bit that you need to know about alloys. Okay, they form... We'll talk about this again in class, just because this is a kind of the weird different things. An alloy is a solution of metals. Okay, so it's like a metal dissolved, a solid dissolved in a solid. So the idea here is that there's two types of alloys. There's interstitial and there's substitutional. Okay, and it depends. Okay, so an example of an alloy that you probably know is sterling silver, 14 karat gold, 18 karat gold, brass, bronze. Those things that are metals, but they're not on the periodic table, are usually a mix of them. Okay, so a substitutional alloy is something like this. All right. That's a substitutional alloy, and what do you need to know about them? You need to, oh, that was interesting. Let's move you up. Okay. You need to know that they're, the radii of the metals are similar. Okay, the radii of the metals are similar. Okay, the blue ones are similar in size to the black ones. So instead of just distorting them or like getting in the way, I think about like the Princess and the Pea, what they do is they replace them. So instead of there being a black one here, there's the blue one. Okay, so let's say maybe the black ones are silver and the blue ones are copper. Let's assume that they have a really similar radius of their atoms, and that is a substitutional alloy. So a copper just takes the place of a silver atom. Interstitial is going to be something like this. I know it's not the world's best drawing. You know I'm not the artist. Okay? You can see that interstitial, you've got maybe like little guys like this, let's say they're carbon, and then you've got the big ones like this, let's say they're iron. That's like stainless steel, or steel even. There's a bigger difference in radii. I spelled that terribly. Oh my goodness, guys, it's been a long break. So the small atoms just sort of fit or attempt to fit in the gaps. That's why steel is stronger than iron, because those carbon atoms kind of displace those iron cores a bit, okay? And since they're displaced, they don't slide past each other so easily. And that's where, remember we talked about how metal is malleable, okay? We said metal's malleable, right? Because those positive cores give up their electrons, and the electrons are free to move about the cabin, and those moving electrons are the moving charged particles, which allow metals to conduct electricity, okay? So here what we've got is you've got your carbon atoms kind of getting in the way and displacing those iron atoms a little bit so that those iron atoms can't slide past each other so nicely. When they can't slide past each other so nicely, that makes that's why steel we consider to be so strong. It's not as malleable. It's not as bendable, whereas gold is really strong, is really soft and really malleable because it doesn't have these little guys in there getting in the way. So sometimes we make these alloys, sorry about that, we make these alloys to get some desired properties, to change the properties of the solvent or the metal that's in higher concentration. In this case it'd be silver, in this case it would be iron. We'll talk a little bit more about that in class, but that's kind of the two different types of alloys that you can see. The last thing we need to talk about, properties of solids, is molecular. So this is a molecule. This is something that's covalent, but it is held together by IMFs. We are going to talk about IMFs, and we kind of probably have started it. Our IMF options here are, let me write IMFs again. Nope. Hydrogen bonding, dipole-dipole forces, and dispersion forces. Those are the forces that hold them together. So that when you're actually boiling water, for example, water is your killer example, you are breaking hydrogen bonds as opposed to covalent bonds. Whereas the previous three options, in a network solid, when you boil it or melt it, you're breaking covalent bonds. In an ionic solid, when you boil it or melt it, you're breaking ionic bonds. And in a metallic solid, when you boil it or melt it, you are breaking metallic bonds. Here, you are not breaking covalent bonds, so there's your water, okay? That's an IMF. In fact, that's hydrogen bonding. That's your IMF, and that's what you're breaking. You're not breaking that covalent bond right there. So what do you need to know about molecular things? They are the ones that have low melting points and boiling points. They are soluble if they're polar, usually. Okay, if they're nonpolar, they're usually not soluble. They do not conduct. And the reason they have low boiling points and melting points is because they're held together by IMFs, which are inherently weaker than a standard bond. So how do you know, right? If I give you some properties, how will you know it's molecular? The low melting point, boiling point is what gives it away. Okay. How will you know it's metallic? Oh, that's great. Okay. How will you know it's metallic? Because it conducts as a solid. That's what sets that one apart. Okay. And how will you know it's network? Because you have none of those things, right? You have a high melting and boiling point that doesn't dissolve and doesn't conduct. That's how you'll know it's network based on the properties alone. Take some notes on this, write down some questions. We'll talk about it in class tomorrow. I hope you had a great snow day, a great Thanksgiving, or a happy break, and I'll see you tomorrow.